So, there's this thing most people think they know about how the moon got here. You probably learned it in school, forgot it, then saw it on some documentary and thought, oh yeah, that makes sense. But here's the thing, the actual story is way messier, way more violent, and honestly kind of insane when you really dig into what happened. The moon wasn't just sitting around waiting to be captured. It's not some ancient relic that's been hanging out since the beginning of time doing its thing. What actually happened is one of the most catastrophic events in Earth's history, and we almost didn't survive it. Let me tell you why the scientists who figured this out basically had to convince everyone they weren't completely crazy. About 4.5 billion years ago, and I know that's a number that's hard to even conceptualize, so just sit with that for a second, our solar system was basically a cosmic demolition derby. Picture it like this. You've got all this dust and debris floating around, and gravity is just aggressively pulling everything together into clumps. Some clumps get bigger, some clumps collide with other clumps, and occasionally you get absolutely catastrophic impacts that change everything. Earth at that time wasn't the solid, stable planet you're living on right now. It was still forming, still pulling in material, still getting hammered by asteroids and space rocks constantly. The early solar system was a genuinely hostile place. And then something happened that would fundamentally reshape what our planet would become. A Mars-sized object, and when I say Mars-sized, I mean roughly the size of the planet Mars, which is about half the diameter of Earth, was hurtling through space on a collision course with our young planet. We call this object Theia, named after the Greek Titaness, who was the mother of the moon in mythology. But unlike the myth, this wasn't some gentle creation. This was impact physics at the most extreme scale. Here's where this gets genuinely wild, and why I want to pause for a second because this is actually mind-bending. When Theia hit Earth, it didn't just bounce off or create some crater. It hit at an angle, not head-on, but at an oblique angle. And when something that massive hits something that massive at those speeds, the energy released is so incomprehensibly large that it's almost meaningless to try to describe it in normal terms. We're talking about temperatures that exceeded what exists anywhere in the universe today. We're talking about the complete vaporization of rock. And here's what happened next that would change everything about why we're even having this conversation right now. The impact was so violent, so catastrophically energetic, that it didn't destroy Earth. Instead, it fundamentally altered it. The collision ejected a massive amount of material, mostly from Theia, but also from Earth's outer layers, directly into orbit around Earth. This debris field wasn't organized. It wasn't neat. It was a chaotic cloud of vaporized rock, liquid metal, and planetary material just spinning around our planet in the aftermath of the most violent collision you could possibly imagine. And that cloud of debris, that's what became the moon. Now, before you think I'm just throwing out a wild guess here, let me explain why scientists are actually confident about this, because for a long time, this theory seemed completely nuts. In the 1970s, a scientist named William Hartmann and his colleague Donald Davis proposed this giant impact hypothesis. And I mean, you can imagine how that went over. People were like, so you're telling me the moon came from a collision? That's your theory. But here's the thing that made them look like geniuses. The data started backing them up in ways nobody expected. When Apollo astronauts brought moon rocks back to Earth in the late 60s and early 70s, scientists could analyze them directly. They could measure isotopes, understand the composition, figure out the age of the rocks. And something really strange showed up in the data. The moon's composition was almost identical to Earth's composition. Not completely identical, there are differences, but way more similar than anyone expected if the moon had just been some random asteroid captured by Earth's gravity. If the moon was just a captured object from elsewhere in the solar system, you'd expect it to have a pretty different composition. But instead, it looked like the moon was made of the same stuff as Earth. That's weird. That's really weird. Unless it literally came from Earth, or more accurately, came from the material that was part of Earth and Theia's collision. Here's the other thing that made scientists start taking this seriously: angular momentum. Wait, stick with me on this because it actually explains something obvious once you understand it. The Earth rotates, right? You know that. The moon orbits Earth. You know that too. But here's what's kind of strange when you actually do the math. If you calculate all the angular momentum, basically all the rotational and orbital energy in the Earth-Moon system, it's massive. Way bigger than you'd expect if the moon was just some random object that got captured. But if the moon was created from debris ejected by a giant impact, that actually explains the angular momentum perfectly. The collision would have imparted massive amounts of rotational energy to both the newly formed Earth and the debris cloud that would become the moon. The math works out. The physics works out. And that's when scientists started getting actually convinced this wasn't just a wild theory. This was probably what actually happened. But now, here's where it gets even more interesting, because the real question isn't just how was the moon created? It's how did we survive this and end up in a solar system where life could eventually exist? Because here's the reality check. If that impact had happened at a slightly different angle, at a slightly different speed, at a slightly different time when Earth was in a different position, everything could have been completely different. Earth could have been obliterated entirely. The debris could have dispersed instead of coalescing into the moon. Or the impact could have been so violent that it stripped away our atmosphere entirely, and we'd have ended up like Mars, a dead, barren rock. There's actually a narrow range of impact parameters where this collision creates a moon and leaves Earth intact enough to eventually become habitable. And we hit that range, which is either the craziest coincidence or it tells us something about how common these kinds of impacts are in planetary formation across the universe. Scientists have run computer simulations of this impact thousands of times now, trying different angles, different speeds, different compositions, and most of the time, the simulation produces a result that looks pretty similar to what our moon actually is. Sometimes the simulations produce a moon that's too small. Sometimes it's too large. Sometimes the debris field doesn't coalesce properly. But when you dial in the parameters that match what we actually observe about the moon, you get a giant impact scenario. Now I know what some of you are thinking. Okay, so the moon came from a collision, but how does that actually happen? Like, how does a cloud of vaporized rock become a solid object? That's actually a great question because it involves some really interesting physics about how gravity and thermodynamics work together. Right after the impact, you've got this debris disk, essentially a ring system like Saturn, but made of actual planetary material. Some of this material is still hot, some is cooling, some is still partially vaporized, and gravity, being the relentless force that it is, starts pulling all this material together. It's like you took all the grains of sand on a beach, threw them up in the air, and gravity is just inexorably pulling them back together. But here's the thing, as material clumps together, it gets hotter. Gravity actually heats material as it collapses inward. There's this principle called gravitational potential energy, and as you compress material, all that potential energy gets converted into heat. So you've got this growing clump of moon stuff that's getting larger and hotter as more material accretes onto it. Eventually, you reach a point where the clumping has stabilized enough and cooled enough that you have a solid object, but this isn't some quick process. This takes time. We're talking weeks to months of continuous accretion before you have something that looks like an actual moon. And here's something that kind of blows people's minds once they learn it. The early moon was much, much closer to Earth than it is now. When the moon first formed from this debris disk, it was probably only about 15,000 to 20,000 kilometers away from Earth. That might sound far, but in cosmic terms, that's actually really close. For comparison, the moon today is about 384,000 kilometers away. So the early moon was roughly 20 times closer, which means, and this is where you can really visualize how insane this would have been. If you were standing on Earth back then and looked up at the sky, the moon would have looked absolutely enormous. Not just big like it looks to us now, genuinely impossibly huge. The angular size would have been so large that it would have dominated your entire sky. It would have probably been terrifying, and the gravitational effects would have been insane too. The tidal forces, the forces caused by the moon's gravity pulling on Earth's oceans and crust, would have been extraordinarily powerful. We're talking about tides that were probably hundreds of meters high. The entire ocean would have sloshed back and forth with incredible violence. The crust itself would have been deforming and flexing. It would have been an actively hostile environment. But here's what's actually fascinating about this. Those tidal forces, as violent as they were actually dissipating energy. As the moon pulled on Earth's oceans, friction caused those tidal forces to gradually slow down Earth's rotation. At the same time, through a quirk of orbital mechanics called tidal locking, the moon was slowly being pushed outward, away from Earth. So over billions of years, the moon has been gradually receding from Earth. It's moving away from us at a rate of about 3.8 centimeters per year. That's incredibly slow on a human timescale, but over billions of years, it adds up. The moon has moved from being 15,000 kilometers away to being 384,000 kilometers away. And as it moved away, Earth's rotation slowed down. Here's something you probably didn't think about. The day used to be much shorter. When the moon was young and close to Earth, a day on Earth might have been only about 5 or 6 hours long. The Earth was spinning much faster. But the moon's gravity gradually slowed that rotation, and today a day is 24 hours. In the distant future, we're talking billions of years from now, a day will be even longer. And actually, this process is still happening. The moon is still slowly moving away from Earth. In billions of years, the moon will be so far away that it will appear smaller in the sky, and total solar eclipses will eventually become impossible because the moon won't be large enough to completely block the sun. So the relationship between Earth and moon isn't static, it's dynamic, it's always been changing, and it will continue to change for as long as both objects exist. But here's what's really interesting about all of this, and why this matters beyond just being a cool space fact. This collision, this violent impact that created the moon, it might have actually been necessary for life to eventually exist on Earth. I know that sounds dramatic, but stay with me because the reasoning is actually pretty sound. The giant impact did several things to Earth that seem bad, but were actually necessary for a habitable planet. First, it created the moon, which stabilizes Earth's axial tilt. See, the angle at which Earth tilts relative to the Sun, that axial tilt of about 23.5 degrees, that's what gives us seasons. But without the moon, that tilt would be unstable. It would wobble wildly over time, potentially swinging from 0 degrees to 50 or 60 degrees. That would create climatic chaos. Seasons would be unpredictable. Some eras would be stable, others would be absolutely unlivable. The moon's gravity helps stabilize Earth's tilt, keeping it relatively constant over geological timescales. That stability is actually really important for the development of stable climates that life could evolve in. Second, the collision brought in a lot of material. That material wasn't just moon stuff, some of it got incorporated into Earth. The impact brought in elements, brought in volatiles like water and carbon dioxide. Some scientists argue that impacts like this and the material they brought to Earth contributed significantly to the chemistry that would eventually lead to life. Third, and this is something that's less well known, the collision essentially reset Earth's magnetic dynamo. Earth has a magnetic field generated by the movement of liquid iron in the outer core. That magnetic field is incredibly important because it shields us from solar radiation. Without it, the solar wind would gradually strip away the atmosphere. We'd end up like Mars, a dead world. The impact didn't just stir the pot, it may have solved a power problem. Earth's magnetic field is generated by a geodynamo, the churning of liquid iron in the core. Some models suggest that the sheer energy of the Theia impact, followed by the moon's early intense tidal tugging, kept Earth's core hotter and more turbulent than it would have been otherwise. This extra stirring ensured our magnetic shield remained strong enough to deflect the solar wind, preventing our atmosphere from being stripped away like Mars was. The giant impact likely disrupted Earth's interior, creating a more vigorous circulation of material in the core, which led to a stronger magnetic field. Some researchers think that without this impact, Earth might not have developed or maintained a strong enough magnetic field to protect life. So the thing that nearly destroyed the planet might have actually been essential for making the planet habitable. That's the kind of cosmic irony that makes you think about how fragile and contingent existence really is. Now, there's something else about this impact that I want to dig into because it relates to one of the biggest questions in planetary science. How common are giant impacts like this? If you look at computer simulations of planetary formation across the universe, giant impacts seem to happen pretty regularly. In fact, they might be almost inevitable. When you've got a solar system forming, you've got all these planetary embryos, protoplanets, floating around and colliding. Some of them merge together. Some of them get ejected. Some of them collide catastrophically. Giant impacts seem to be a natural part of how planetary systems evolve. This means that Earth might not be unique in having experienced a giant impact. In fact, Mars probably experienced giant impacts. Venus probably did too. Jupiter and Saturn have definitely experienced massive collisions. It might just be part of how planets form and evolve. But here's what's interesting. Not all giant impacts result in a moon. The conditions have to be pretty specific. The impact has to be at the right angle, the right speed, and the impactor has to be the right size. Too small, and you don't eject enough material. Too large, and you destroy the planet. Miss the angle and the debris doesn't coalesce properly, which raises a question that scientists actually debate. How many planets out there have moons as a result of giant impacts? And if moons are necessary for habitability, because of the axial tilt stabilization and magnetic field effects, then how many habitable planets might exist with moons? This connects to something called the rare Earth hypothesis, which is basically the idea that habitable planets like Earth might be actually pretty rare. Not impossible, but rare. And one of the reasons they might be rare is because they need to have experienced a giant impact at just the right parameters, leading to a moon, which then stabilizes the climate and protects the magnetic field. It's kind of a humbling thought. Your existence depends on a violent cosmic collision happening at precisely the right moment in precisely the right way billions of years ago. If any of those parameters were slightly different, you wouldn't be here. But let me get into some of the actual details about what we know about the collision itself, because there are some genuinely fascinating specifics that scientists have worked out. The impactor, Theia, was probably formed somewhere in the inner solar system, maybe in a region where Mars-sized objects were common. When I say Mars-sized, I'm talking about something with a mass of roughly 0.1 times Earth's mass. So if Earth weighs 6 sextillion tons, Theia probably weighed around 600 quintillion tons. These are numbers that are basically incomprehensible, but the point is, Theia was genuinely enormous. The collision probably happened about 4.51 billion years ago, based on dating of lunar rocks and meteorites. But here's something interesting. We can't pinpoint it to an exact date. We're talking about a range of maybe a few million years. That might sound precise, but in cosmic terms, that's actually pretty fuzzy. The impact velocity was probably somewhere in the range of 4 to 6 kilometers per second. For reference, that's roughly 15,000 kilometers per hour. It's fast. It's incredibly fast. At that speed, the kinetic energy of the collision was so massive that it doesn't even make sense to describe it in conventional terms. Some estimates put the energy at around 10 to the 34th power joules. To put that in perspective, that's roughly 10 billion times the energy of the largest nuclear bomb ever detonated. The largest nuclear bomb was the Tsar Bomba, detonated by the Soviet Union in 1961. It had a yield of about 50 megatons of TNT. The collision was billions of times more powerful. What happens at impact is something called hypervelocity collision physics. At those speeds, materials don't behave the way you might intuitively expect. Metal and rock don't just crumple like a car crash. Instead, they liquefy, they vaporize. The material at the impact point becomes essentially a plasma, a superheated state of matter where electrons are stripped from atoms. The impact created what's called an impact plume, essentially a massive jet of vaporized and liquefied material that shot upward and outward from the impact site. This plume contained material from both Theia and from Earth's outer layers. The plume expanded, cooled slightly, and then began to condense as it traveled away from the impact site. Some of this material was ejected so forcefully that it escaped Earth's gravity entirely and just drifted off into space. Some of it was ejected at slightly lower velocities and ended up in orbit around Earth. It's this orbital material that would eventually form the moon. Now here's something that took scientists a while to figure out, and it actually relates to one of the major criticisms of the giant impact hypothesis: the moon's composition. If the moon formed from debris ejected during an impact, you'd expect it to contain a lot of material from Theia. But as I mentioned earlier, the moon's composition is almost identical to Earth's composition. It has the same oxygen isotope ratios, the same tungsten isotope ratios, the same ratio of iron to silicates. This is actually really, really similar. When scientists talk about these chemical signatures, They are specifically looking at oxygen isotopes, specifically oxygen 17 and oxygen 18. In the solar system, these isotopes act like a cosmic zip code. Mars has its own ratio. Meteorites from the asteroid belt have another. If Theia had formed in a different part of the solar system, it should have had a different oxygen fingerprint. The fact that the moon's oxygen ratio is identical to Earth's, to within parts per million, is what forced us to move past the simple collision theory and toward the more radical synestia model. So, how does that work? If most of the ejected material came from Theia, why does the moon look like it came from Earth? Well, there are a few possible explanations, and scientists have been debating them for years. One explanation is that Theia itself had a composition that was almost identical to Earth's composition. Maybe Theia formed in the same region of the solar system and accreted material from the same sources. If that's the case, then debris from Theia would naturally have a similar isotope composition to Earth. Another explanation that's gained more traction recently is that most of the material in the moon actually did come from Earth's outer layers, not from Theia. The impact might have been violent enough to vaporize Earth's mantle, the layer of rock beneath Earth's crust, and eject a significant portion of it into orbit. Theia's material would have been mixed in, but the sheer volume of Earth's material being ejected would have dominated the composition of the debris disk. This actually changes the picture of the collision somewhat. Instead of two planets colliding and mixing their material equally, it might have been more like Theia hit Earth so hard that it stripped away Earth's outer layers, and those outer layers became the moon. But the moon couldn't just form anywhere. It had to respect a mathematical boundary called the Roche limit. This is the distance, roughly 11,000 miles from Earth's center, where a planet's tidal forces are so strong they would rip a moon apart. The debris from our collision had to migrate past this invisible line before gravity could win the tug of war against tidal shredding. Everything inside the Roche limit fell back to Earth or stayed as a ring. Everything just outside it began to clump together into the sphere we see today. There's actually a newer variation on the giant impact hypothesis called the synestia model, proposed by planetary scientist Sarah Stewart. A synestia is essentially a giant cloud of vaporized material that forms when two planetary bodies collide with enough energy. Instead of immediately forming a debris disk that coalesces into a moon, the impact creates this massive swirling cloud of vaporized rock and metal that surrounds Earth. In the synestia model, Earth and the moon to be were essentially part of the same giant vaporized structure immediately after the collision. They weren't separate objects yet. They were both part of this enormous rotationally flattened cloud of hot material. Over time, and we're talking maybe a few years, this synestia would cool and condense and eventually separate into Earth and the moon. This model actually explains the compositional similarity between Earth and the moon better than the original giant impact hypothesis, because Earth and the moon literally came from the same vaporized material. They were the same object, just temporarily. The synestia model is still relatively new. It was proposed in 2012, but it's gained a lot of support from simulations and from the data we have about the moon's composition and formation. Now, here's something that a lot of people don't think about. What happened to Theia after the collision? This is actually a pretty interesting question, and the answer is it got completely incorporated into either Earth or the moon. Theia didn't survive as a separate object. After the impact, Theia's material was mixed into the debris cloud that became the moon, and some of it probably got incorporated back into Earth as well. There was actually a study published a few years ago that suggested Theia's core might have sunk into Earth's mantle. See, Theia would have had an iron core, similar to Earth. When the collision happened, the kinetic energy was so enormous that Theia essentially disintegrated. Its material was scattered and vaporized. But Theia's iron core, the densest part of the planet, might have had enough coherence to sink through the vaporized material and eventually merge with Earth's core. If that's true, then Earth's core today contains material from both Earth and Theia. Your planet is literally a hybrid between two ancient planets. The iron beneath your feet has atoms that came from Theia billions of years ago. This is one of those facts that seems almost abstract until you actually think about it, and then it gets kind of wild. The ground beneath you contains the literal remnants of an ancient planetary collision. Now let me talk about what the early moon looked like, because it was genuinely very different from the moon we see today. The early moon was hotter, much hotter. Immediately after formation, it was still radiating heat from the collision and from the gravitational compression that created it. The surface was probably molten, liquid rock covering the entire sphere. Scientists call this the magma ocean phase. The entire moon was essentially an ocean of liquid rock. Over time, and we're talking maybe hundreds of thousands of years, the surface began to cool and solidify. The first solid crust formed on the moon, but it wasn't stable. The interior of the moon was still hot and convective. There was massive volcanism. The early moon was geologically active in a way that today's moon simply isn't. Actually, the moon was probably more geologically active than Earth during this period, which is kind of surprising when you think about it. The moon is smaller, so it should cool faster and become geologically dead sooner, right? But the early moon had all this gravitational and tidal heating from its proximity to Earth. That heat kept the moon active for a surprisingly long time. The volcanism on the early moon created vast lava flows. These flows filled in large basins and created what would eventually become the dark regions on the moon that we call Maria, Latin for seas. Galileo named them seas because he thought they were actual oceans of water, but they're actually just flat plains of solidified lava. The moon's volcanic activity probably peaked around 3 billion years ago and then gradually declined. By about 1 billion years ago, the moon had cooled enough that most volcanism had stopped. Today, the moon is essentially geologically dead. There's almost no tectonic activity. There's almost no volcanism. It's a quiet, stable body. But the evidence of its violent past is written all over its surface. The craters covering the moon, thousands upon thousands of craters, those are impact scars from billions of years of bombardment by asteroids and meteorites. The moon doesn't have an atmosphere to burn up incoming objects like Earth does, so everything that hits it leaves a mark. Speaking of atmosphere, let me address something. Could the moon have retained an atmosphere after formation? The answer is basically no. The moon is much smaller than Earth, which means it has lower gravity. At lower gravity, gas molecules can escape to space more easily. There's a concept called the escape velocity, the speed at which an object needs to travel to escape a planet's gravity entirely. Earth's escape velocity is about 11 kilometers per second. The moon's escape velocity is only about 2.4 kilometers per second. That's a huge difference. At high temperatures, molecules of gas move faster. The hotter the atmosphere, the more likely molecules are to be moving fast enough to escape. For the moon, even relatively cool atmospheric temperatures would result in gas molecules moving fast enough to escape. Additionally, the moon would have been exposed to the solar wind. the stream of charged particles constantly flowing outward from the sun. Without a strong magnetic field to deflect this solar wind, any atmosphere would gradually be stripped away. So even if the moon somehow had an atmosphere early on, it would have lost it pretty quickly. The moon has been atmosphereless for essentially its entire history. But here's a fascinating detail that I want to dig into because it connects back to Earth and the role the moon played in life's eventual emergence. The collision might have actually brought water to Earth. One of the biggest mysteries in planetary science is, where did Earth's water come from? Water is essential for life, but it's actually kind of rare in the inner solar system. Most of the water in the solar system is farther out, in regions like the asteroid belt or beyond. So how did Earth, located relatively close to the sun, end up with massive oceans of water? There are a few theories. One is that water was incorporated into Earth's material during formation from carbonaceous chondrite meteorites that contained water. Another is that water was delivered to Earth by comets or asteroids after the planet had already formed. But here's an interesting possibility. The giant impact might have played a role. Theia probably contained some water in its material. Additionally, the collision might have created conditions that allowed Earth to capture water-rich asteroids and comets more effectively. The impact created a debris disk with a lot of gravitational influence, which could have shepherded more water-bearing material toward Earth. It's not like the impact directly created water. Water is just hydrogen and oxygen bonded together, and both of those elements were present in the early solar system. But the impact might have influenced how much water ended up on Earth. And that's actually kind of important for the story of how life emerged. Without the right amount of water, Earth would be a desert. With too much water, the entire planet might be covered in a global ocean with no land. Earth ended up with the Goldilocks amount, enough water to have oceans and support life, but not so much that there's no dry land. And the giant impact might have played a role in achieving that balance. Now, I want to talk about some of the implications of all this, because understanding how the moon formed actually tells us something important about how rare or common habitable planets might be in the universe. The standard narrative about habitable planets goes something like this. You need a planet in the habitable zone around a star, close enough to be warm, but far enough to not be scorched. You need the right size so it can retain an atmosphere. You need the right composition. That's the basic checklist. But if you add the moon requirement, if you say that a stable climate requires a large moon that's formed through a giant impact at just the right parameters, suddenly the checklist gets a lot longer. You need all the previous conditions, plus you need a giant impact at the right time with an impactor of the right size and composition. That's genuinely restrictive. This is why some scientists argue that Earth might not be completely typical. We might be on the lucky end of the spectrum, a planet that happened to have the right conditions for life, not just in terms of temperature and atmosphere, but also in terms of moon formation and climate stabilization. Does this mean habitable planets are incredibly rare? Not necessarily. It means they might require a specific set of conditions that aren't guaranteed. Some planets might achieve habitability through different mechanisms. Some might not need a large moon to stabilize their climate. Some might be in binary star systems where gravitational influences from a companion star serve a similar stabilizing function. But it does suggest that the path to a habitable planet like Earth isn't inevitable. It requires luck. It requires specific conditions to align. And that's actually a humbling realization. Here's another implication that's kind of interesting. If giant impacts are necessary for moon formation, and if moons are common around habitable planets, then we might expect to find a lot of exoplanets with moons. But detecting moons around distant exoplanets is incredibly difficult. We can detect exoplanets by seeing how they dim the light of their star as they pass in front of it. But detecting a moon around an exoplanet requires even more precision. We'd need to see the subtle gravitational variations caused by the moon. As our detection technology improves, we might start discovering exomoons, moons around exoplanets. And if we find them, we might learn something about how common giant impacts are in other solar systems. If moons are everywhere, that tells us one thing. If moons are rare, that tells us something else. Actually, there's a team of astronomers actively working on this problem right now. They've developed methods to detect exomoons, and they're analyzing data from various exoplanet systems looking for signs of moons. It's one of the frontiers of exoplanet science. Now let me address something that a lot of people wonder about. Could the collision happen again? The short answer is no. The conditions that led to the giant impact with Theia were specific to the early solar system when there were a lot of planetary embryos floating around. Those conditions no longer exist. The solar system has stabilized. The major planets are in stable orbits. There are no more Mars-sized objects wandering around in the inner solar system that could collide with Earth. But here's the thing, smaller impacts still happen. Earth is constantly being hit by asteroids and meteorites. Most of them are small, pebbles or dust, but occasionally larger asteroids hit. The asteroid that wiped out the dinosaurs 66 million years ago was roughly 10 kilometers in diameter. That's genuinely massive, but it's still minuscule compared to Theia. Could another giant impact happen in the distant future? Theoretically, if the orbits of the planets were perturbed, if something disrupted the current stable configuration, then maybe. But the timescale for that would be so enormous that it's basically not worth worrying about. We're talking about millions or billions of years of stable orbits before any chaotic behavior might emerge. In practical terms, for the foreseeable future, meaning the next few billion years, Earth is safe from giant impacts. The Moon, on the other hand, is still being hit regularly. The craters on the lunar surface testify to that ongoing bombardment. Okay, let me shift gears here because there's something about the Moon's effect on Earth that I want to explore in more detail. The Moon doesn't just stabilize Earth's axial tilt, it also affects Earth's oceans, and that effect is way more consequential than most people realize. Tides are caused by the Moon's gravity pulling on Earth's oceans. The ocean on the side of Earth facing the Moon experiences a gravitational pull, which causes the water to bulge toward the Moon. At the same time, the ocean on the opposite side of Earth also bulges, and here's the counterintuitive part, because of centrifugal effects as Earth and Moon orbit around their common center of gravity. The result is that Earth's oceans bulge in two directions simultaneously, toward the Moon and away from the Moon. As Earth rotates beneath these bulges, different parts of the coastline experience these bulges passing overhead, resulting in tides. Most places on Earth experience 2 high tides and 2 low tides every day. The tides are powerful. They create currents that mix ocean water, distributing nutrients and heat. They drive waves that shape coastlines. Early tidal forces were so powerful that they influenced how life evolved in the oceans. Tidal zones, the areas between high tide and low tide marks, are challenging environments where organisms had to adapt to constant changes in water level and exposure to air. Some of the earliest complex life evolved in these tidal zones. Additionally, tides might have played a role in the origin of life itself. Some scientists have proposed that tidal pools, isolated pools of seawater left behind when the tide recedes, could have been environments where chemical reactions that led to life could occur. The repeated concentration and dilution of chemicals in tidal pools might have created conditions favorable for the emergence of self-replicating molecules. It's speculative, but the idea is intriguing. The moon might not just have stabilized Earth's climate, it might have also actively contributed to the emergence of life through tidal processes. Now, here's something that's less well known. The tides are actually slowing down Earth's rotation, and the moon is slowly moving away. And these two processes are connected through conservation of angular momentum. When the moon pulls on Earth's oceans through tidal forces, friction in the ocean basins dissipates energy. This energy comes from Earth's rotation, so Earth's rotation gradually slows down. But here's the thing. Angular momentum is conserved. If Earth's rotational angular momentum decreases, that momentum has to go somewhere, and it goes into the moon's orbital angular momentum. What that means, in practical terms, is that as Earth's rotation slows, the moon moves into a higher orbit. It's like a figure skater spinning and extending their arms. As they extend their arms outward, they spin slower. Similarly, as angular momentum is transferred from Earth's rotation to the moon's orbit, the moon moves outward. This process will continue for billions of years. Eventually, Earth's rotation and the moon's orbit will reach a state called tidal locking, where one rotation of Earth equals one orbit of the moon. At that point, the same side of Earth will always face the moon, the same way the same side of the moon always faces us today. The moon is tidally locked to Earth, but Earth is not yet tidally locked to the moon. But that won't happen for a very, very long time. By that point, the sun will probably have expanded into a red giant and consumed Earth. So we don't have to worry about that outcome. Actually, here's something wild to think about. The moon has been the most constant and predictable thing in Earth's sky for 4.5 billion years. It's been a reference point for every species that's ever evolved on Earth. Ancient humans used the moon to mark time. The lunar cycle, the roughly 29.5-day cycle of the moon's phases, is so fundamental that it influenced how humans organize society. Many cultures base their calendars on lunar months, but that constancy is an illusion. The moon is slowly changing. It's moving away. The tides are getting weaker. Eventually, over time scales of hundreds of millions of years, the effects will become noticeable. The moon will be visibly smaller in the sky. The tides will be weaker. But by then, presumably, life on Earth will have evolved and changed in ways we can't currently imagine. Or, humanity will have figured out how to leave the planet and spread to other worlds. That's another possibility that's probably worth thinking about. Let me talk about some of the specific evidence that strengthened the giant impact hypothesis over the years, because this is actually pretty interesting from a scientific methodology perspective. One of the major pieces of evidence came from lunar samples returned by Apollo astronauts. When scientists analyzed these samples, they found that the moon rocks contained volatile elements in much lower concentrations than Earth rocks. Volatile elements are elements that evaporate at relatively low temperatures. Examples include water, potassium, and other light elements. Why is this significant? Well, if the moon formed from a giant impact that vaporized material, it would have lost a lot of its volatile elements as they boiled away into space. The hotter the impact, the more volatiles would be lost. So the fact that the moon is depleted in volatile elements compared to Earth makes sense in the context of a giant impact scenario. Another piece of evidence is the moon's magnetic field history. Ancient lunar samples show evidence of a strong magnetic field in the early moon, but this field gradually weakened and eventually disappeared. This pattern is consistent with the moon cooling down over time and the convection in its interior decreasing. It's not consistent with the moon being a captured asteroid, which wouldn't have experienced this particular thermal evolution. There's also the isotopic evidence I mentioned earlier. Different elements have different isotopes, variants with different numbers of neutrons. The ratios of these isotopes vary depending on the environment where the material formed. The fact that Earth and the Moon have nearly identical isotopic ratios for oxygen, tungsten, and other elements is really hard to explain unless they came from the same material source. If the Moon were a captured asteroid from elsewhere in the solar system, you'd expect isotopic differences. But the similarity suggests a common origin, which points to the Moon forming from debris ejected from Earth during an impact. There's also the angular momentum argument I mentioned earlier. If you calculate the total angular momentum in the Earth-Moon system and work backward, you end up with parameters consistent with a giant impact. It's not a perfect match. There are still details to work out, but it's close enough to be compelling. And then there are the computer simulations. Scientists have run thousands of simulations of planetary formation and giant impacts. When you set the parameters to match what we observe about Earth and the Moon, the simulations consistently produce a result that looks like a giant impact with a Mars-sized impactor. The consistency across different simulations is pretty compelling. Actually, I want to dig into the simulations a bit more because they're kind of fascinating from a computational perspective. Running a simulation of a giant impact is genuinely computationally intensive. You have to model the behavior of material under extreme conditions. You need to account for the vaporization of rock, the creation of a plasma, the dynamics of the debris disk. You need to use fluid dynamics equations, gravitational calculations, thermodynamics, all simultaneously. The resolution of these simulations has improved dramatically over the years. Early simulations in the 1970s and 1980s were relatively crude. They could capture the broad outlines of what happened, but they couldn't resolve fine details. Modern simulations have millions or billions of particles representing different chunks of material. The resolution is high enough to realistically simulate what happens during and after the impact. What's interesting is that when you run these simulations with different parameters, different impact angles, speeds, impactor sizes, you get different outcomes. Most outcomes don't produce a stable moon. Some produce a moon that's too small. Some produce a moon that's too large. Some produce a debris disk that doesn't coalesce properly. But when you dial in the parameters to match real observations, a Mars-sized impactor hitting at a slightly oblique angle at a speed of around 4 to 6 kilometers per second, you get an outcome that produces a moon remarkably similar to our actual moon. That consistency is hard to chalk up to coincidence. It suggests that the giant impact hypothesis is capturing something real about what actually happened. Now, there's a question that might occur to you. If giant impacts are part of how planetary systems form, why doesn't every planet have a moon? That's actually a great question, and the answer involves some really interesting dynamics about how planetary systems evolve. First, not every planetary body experiences a giant impact. The conditions have to be right. You need planetary embryos of the right size wandering into collision courses. Not all planetary systems have those conditions. Second, even if a giant impact happens, it doesn't always produce a moon that survives. Sometimes the impact ejects material, but that material doesn't coalesce into a stable moon-sized object. Sometimes the debris disk is unstable and material either falls back into the planet or escapes into space. Sometimes a moon does form, but it's so close to the planet that tidal forces gradually pull it apart and it gets destroyed. Third, some moons that do form might be lost through various mechanisms over time. A moon could potentially be ejected from orbit through gravitational interactions with other bodies, or it could gradually spiral into the planet and collide with it, or it could be captured by another body. These are all possible outcomes, though less likely once a planetary system reaches a stable configuration. Additionally, there's a selection effect at play here. We're biased toward observing planets that have moons, at least in terms of our own solar system. We live on a planet with a moon, and we've become familiar with how that works. But in other solar systems, there might be plenty of planets without moons, and we just don't pay as much attention to them because they're not as interesting to us. Actually, when you look at our own solar system, not all planets have moons, or they have moons that formed through different mechanisms. Mercury and Venus don't have moons. Mars has two small moons, Phobos and Deimos, which were probably captured asteroids rather than formed through giant impacts. Jupiter and Saturn have large moon systems, which might have formed through giant impacts or through other mechanisms like capture. Neptune has a large moon called Triton that was definitely captured. It orbits in the opposite direction from Neptune's rotation, which is a dead giveaway that it wasn't formed in place. So moon formation is not a universal process. It's specific to certain planetary systems and certain conditions. All right, let me talk about something that's kind of fascinating: the potential habitability of moons themselves. Europa, one of Jupiter's moons, has a subsurface ocean of liquid water beneath its icy crust. Enceladus, one of Saturn's moons, also has a subsurface ocean. Titan, another moon of Saturn, has liquid methane and ethane lakes on its surface, and probably a subsurface water ocean as well. These moons might be habitable, not because they're like Earth, but because they have liquid water and energy sources. The energy comes from tidal heating, the same mechanism that causes tidal friction on Earth. Except on these distant moons, tidal heating is keeping the subsurface oceans liquid despite being far from the sun. Isn't that fascinating? The same tidal forces that the moon creates on Earth, creating the tides we see in our oceans, also create heating in these distant moons, potentially sustaining habitable environments. It's a different manifestation of the same physical principle. And here's where this connects back to the giant impact. If giant impacts are necessary for moon formation, and if moons can create habitable environments through tidal heating, then giant impacts might indirectly lead to habitable conditions in multiple places, not just on the primary planet, but also on the moons around it. This expands the potential for life in the universe. It's not just about planets in habitable zones. It's also about moons around gas giants, which might be far from their star but still habitable because of tidal heating from their primary. Now, there's something I want to address that sometimes comes up when people talk about the moon's formation: the capture hypothesis. For a long time, before the giant impact hypothesis gained widespread acceptance, scientists considered alternative explanations for the moon's origin. One was the capture hypothesis, the idea that the moon formed elsewhere and was captured by Earth's gravity. Why doesn't this work? Well, there are several problems. First, orbital mechanics makes it really hard to capture a large body like the moon through gravity alone. You'd need some mechanism to dissipate energy and slow the moon down enough for it to enter orbit. That's not impossible, but it's complicated. Second, The isotopic evidence doesn't support it. If the moon formed elsewhere in the solar system, it should have a different isotopic composition than Earth. But it doesn't. The isotopic similarity strongly suggests a common origin. Third, the capture hypothesis has trouble explaining the angular momentum. If the moon were captured, the angular momentum of the system would be different from what we actually observe. So while the capture hypothesis is theoretically possible, the evidence doesn't support it. The giant impact hypothesis is much more consistent with what we actually observe. There's also been something called the co-accretion hypothesis, which suggested that Earth and the Moon formed together in orbit around the Sun from the same disk of material without requiring a giant impact. But this hypothesis has pretty much been abandoned because it has trouble explaining several aspects of the Earth-Moon system, particularly the isotopic compositions. The giant impact hypothesis has become the consensus among planetary scientists, and for good reason. It explains more of the observations more consistently than alternative hypotheses. Okay, let me get into some of the really cool details about the physical state of the moon immediately after formation. Right after the collision, the moon was extraordinarily hot. Estimates suggest surface temperatures in the range of 1,200 to 1,500 Kelvin, roughly 1,000 degrees Celsius. That's hot enough to melt rock. The interior would have been even hotter, probably several thousand degrees Kelvin. At those temperatures, the moon was essentially a giant ball of molten rock, the magma ocean I mentioned earlier. But here's something interesting. Even as a molten body, the moon had structure. There was internal convection, with hot material rising from the interior and cooler material sinking. This convection would have been turbulent and violent. As the surface cooled, lighter minerals would have started to crystallize preferentially. One of these minerals is called plagioclase feldspar. It's a light-colored mineral that's less dense than the molten rock surrounding it. As plagioclase crystallized, it would float to the surface, accumulating in a crust. Over time, and again, we're talking maybe hundreds of thousands of years, this process created a solid crust covering the entire moon. This early crust was called the lunar magma ocean crust, or sometimes the primordial crust. But here's where it gets interesting. This primordial crust didn't last long. Well, relatively speaking, it lasted longer than the formation process, but in geological terms, it was transient. Once the crust had solidified, the moon's interior began a long process of cooling and differentiation. Heavier elements like iron gradually sank toward the center, creating an iron core. Lighter elements accumulated in the mantle and crust. This process took a long time, millions of years, but it was happening. And during this time, the moon was volcanically active. The internal heat created pressure, and that pressure was released through volcanic eruptions. These weren't quiet eruptions. They were explosive. Enormous amounts of lava flowed across the lunar surface, filling in depressions and creating the smooth plains that we call Maria. The volcanism peaked around 3 to 3.5 billion years ago. By that time, much of the moon's internal heat had been radiated away into space, but there was still enough heat to drive ongoing volcanism. After about 1 billion years ago, volcanism essentially stopped. The moon had cooled enough that there wasn't enough internal heat to drive large-scale eruptions. Today, the moon is geologically dead. It's cold. There's no internal heat driving volcanism. There's no tectonic activity. It's just sitting there, orbiting Earth, slowly receding, gradually cooling further. But the evidence of its violent past is everywhere. The surface is scarred with impact craters from billions of years of bombardment. The dark Maria are frozen lava flows. The light highlands are ancient crust from the magma ocean. Everything on the moon's surface tells a story of a dynamic, active world in its distant past. Now, here's a question that connects back to the bigger theme. What can the moon tell us about how other planets and moons form? The moon is relatively accessible to us compared to other bodies in the solar system. We've brought back samples. We've landed rovers and spacecraft on it. We've mapped it in detail. We understand its geology and its history reasonably well. And the story of the moon, that it formed from a giant impact, gives us a template for understanding how other moons might have formed. It tells us that large moons around terrestrial planets might often be products of giant impacts. It tells us that giant impacts aren't just destructive events. They can be creative events that generate new planetary bodies. This has implications for how we think about exoplanets and exomoons. If we discover large moons around exoplanets, we might infer that those exoplanets have experienced giant impacts. That tells us something about the evolution of that planetary system. Additionally, the moon's composition and structure tell us something about what planetary material looks like when it's been vaporized and reformed. This is relevant for understanding how planets form in general and how they undergo chemical differentiation. There's something almost poetic about the fact that we can look at the moon in the night sky, an object that's been constant throughout human history, and read in its surface features the story of a violent cosmic collision that happened billions of years before our species even existed. All right, let me shift to something that's kind of important and doesn't get discussed as much: the cultural and psychological significance of the moon. The moon has been profoundly important to human civilization. It's the brightest object in our night sky after the sun. It's been the subject of myths, stories, and spiritual beliefs across virtually every human culture. Before electric lights, the moon was the only thing that reliably provided nighttime illumination. It shaped how humans organized their time. The word month comes from moon. The lunar cycle, the 29.5-day cycle of lunar phases, is one of the most regular, predictable celestial events. It's visible from anywhere on Earth. It's never ambiguous. Every culture developed an understanding of the lunar cycle and incorporated it into their calendar systems. Many ancient peoples believed the moon had a divine nature. Some saw it as a god or goddess. Some saw it as a guardian or protector. Some used it for spiritual or ceremonial purposes. The fact that the moon regularly disappears and reappears during new moons and full moons made it seem magical. It's actually just the moon's position relative to Earth and sun changing, but before astronomy explained this, it seemed genuinely mysterious. The moon was also practically important. Its light made nighttime travel and work possible. Its gravitational effects on tides were evident to anyone living near the ocean. The tides are so regular that ancient peoples could predict them. And then in 1969, humans actually went to the moon. We landed on it. We walked on it. We brought back rocks. It was one of the most extraordinary achievements in human history, and it fundamentally changed how we thought about the moon. It transformed the moon from a mystical, distant object into a place, a real location that humans could visit. But here's what's interesting. Even after we went to the moon and demystified it to some extent, it maintained its cultural significance. Maybe even more than before. The moon landing showed us that we could achieve extraordinary things. It showed us that our understanding of physics and engineering was sophisticated enough to get us to another world. And understanding how the moon formed, understanding that it came from a giant cosmic collision. that it's a survivor of planetary violence, doesn't diminish its significance. If anything, it deepens it. We understand now that the moon is essential for our existence, not just culturally or spiritually, but physically. The moon stabilizes our climate. The moon creates our tides. The moon's presence has made Earth habitable in a way that most planets aren't. We're not just admiring the moon for its beauty or its light. We can appreciate it as a fundamental part of the system that makes life on Earth possible. Now, let me talk about some open questions in lunar science because the giant impact hypothesis, while widely accepted, still has some details to work out. One question is the exact timing of the giant impact. We know it happened around 4.5 billion years ago, but the precise date is still debated. Different dating techniques give slightly different ages, and there's still room for improvement in our ability to date ancient lunar samples. Another question is the exact parameters of the impact. We know it involved a Mars-sized body, but how massive exactly? How fast was it traveling? What was the exact angle of impact? Simulations can narrow down the range, but there's still uncertainty. There's also the question of where Theia came from. Did it form in the same region of the solar system as Earth or elsewhere? What was its exact composition? These questions have implications for understanding how many Theia-like bodies might form in other planetary systems. There's also ongoing debate about the exact mechanism by which the debris disk coalesced into the moon. The synestia model I mentioned earlier is gaining support, but there are still alternative models being explored. The details matter because they affect our understanding of the moon's composition and thermal history. Another open question is whether the moon captured any volatile-rich material after its formation. We know the moon is depleted in volatiles compared to Earth, which supports the giant impact hypothesis. But the moon does contain some water and other volatiles. Did these arrive after the moon formed, delivered by comets or asteroids? Or were they present in some of the material that accreted onto the moon immediately after the collision? This is still being investigated. There's also the question of the moon's core. We know the moon has an iron core, but how large is it exactly? Is it solid or partially liquid? Does it generate a magnetic field today? These questions have implications for understanding the moon's internal structure and thermal evolution. We have some data from the Apollo missions and from orbital measurements, but higher resolution data would help. One fascinating ongoing investigation involves the lunar samples brought back by Apollo astronauts. Scientists are still analyzing these samples with increasingly sophisticated techniques. New analytical methods, like isotope analysis using more precise instruments, continue to yield new insights about the moon's composition and formation. There's also new data coming from lunar orbiters. Multiple countries have placed orbiters around the moon in recent years, mapping it at higher resolution than ever before. This data is helping us understand the lunar geology and structure in greater detail. And then there's the prospect of future lunar exploration. NASA's Artemis program aims to return humans to the moon in the coming years. Part of the goal is to collect more lunar samples from locations we haven't sampled before. This could yield new insights into lunar geology and formation. There are also plans for lunar rovers and eventually lunar bases. These would allow for much more extensive exploration than was possible during the Apollo missions. With extended time on the surface, we could drill deeper, explore more thoroughly, and collect samples from a wider variety of locations. From a scientific perspective, understanding the moon better has implications beyond just lunar science. It helps us understand planetary formation in general. It helps us understand how habitable planets develop. It helps us think about what to expect when we eventually discover habitable exoplanets and their moons. Okay, let me address something that's kind of a fun thought experiment. Could Earth have ended up with multiple moons? In principle, yes. If multiple giant impacts had occurred, if Earth had been hit by multiple Mars-sized bodies at different times, each impact could have ejected material that coalesced into a moon. We could theoretically have ended up with a multi-moon system like Jupiter or Saturn. In fact, some scientists have speculated that Earth might have had multiple moons at different times in its history. Maybe an early giant impact created the first moon. Maybe that moon was eventually ejected or destroyed. Maybe a later impact created the current moon. But the evidence we have doesn't support this. The current moon appears to be the only large moon Earth has ever had. We don't have evidence of previous moons that were destroyed. The isotopic dating suggests that the moon we have now formed around 4.5 billion years ago and has been here ever since. Could Earth have captured additional moons through gravitational interaction? Theoretically possible, but unlikely. The stability of a multi-moon system depends on the relative orbital parameters. Too many moons and the system becomes unstable. Orbits can cross. Collisions can occur. The system could self-destruct. Earth's single moon system is actually fairly stable and has persisted for billions of years. In some ways, it's ideal. It's large enough to have significant gravitational effects on Earth, but not so large that it creates destabilizing tidal forces. It's at a stable distance that's been gradually increasing over time through the angular momentum transfer mechanism. So in some sense, we got lucky. We got a moon that's just right, large enough to be important, but not so large as to be problematic. And that moon formed through a mechanism, a giant impact, that was violent and unlikely, but apparently not so rare that it's unusual in planetary formation. There's actually an interesting implication of this. If we ever establish a civilization that extends beyond Earth, the moon might become incredibly important as a resource. The moon is close to Earth, only 384,000 kilometers away. By the standards of space travel, that's nearby. It's much closer than Mars or any other body in the solar system. The moon has no atmosphere, so landing and launching from the surface is relatively straightforward compared to planets with atmospheres. The surface has mineral resources that could be extracted and used. There's probably water ice in permanently shadowed craters near the poles. An advanced civilization could potentially mine the moon, build bases there, use it as a launching point for further exploration. Some scientists and engineers have proposed that the moon could become a major hub for space activities in the future. Spacecraft could be built there, fueled there, launched from there. It would be a logical stepping stone for human expansion into the solar system. And all of that is made possible by the fact that the moon exists, that it's close to Earth, that it's large enough and stable enough to be useful, which, when you think about it, all traces back to the giant impact billions of years ago. The violence of the past enabled the possibilities of the future. Now let me talk about something that's kind of profound. The fact that we can understand how the moon formed at all. Think about this. The giant impact happened 4.5 billion years ago. There were no humans around to observe it. There was no technology, no cameras, no instruments. The collision occurred, the debris disk formed, the moon coalesced, and then 4 billion years passed. And yet, using physics, chemistry, and careful observation, we were able to figure out what happened. We analyzed moon rocks and found isotopic signatures. We ran computer simulations and found that they produced outcomes consistent with observations. We measured the angular momentum of the Earth-Moon system and worked backward to find the collision parameters. We synthesized data from multiple independent sources, and they all pointed to the same conclusion. That's actually kind of remarkable. We have this detailed understanding of an event that no one witnessed, that happened before any life existed on Earth, and we derived that understanding through careful scientific investigation. This is the power of science. It's not just about directly observing things. It's about using the evidence left behind by past events to reconstruct what happened. It's about checking multiple independent lines of evidence and seeing if they converge on the same story. And that convergence, that multiple independent methods, all pointing to the giant impact hypothesis, is what gives us confidence that we've actually figured out what happened. Of course, science is also always open to revision. If new evidence emerged that contradicted the giant impact hypothesis, we'd have to reconsider. If the synestia model eventually gained more support than the debris disk model, our understanding would shift. Science isn't about absolute certainty. It's about following the evidence and updating our understanding as new evidence emerges. But right now, the evidence strongly supports the idea that the Moon formed from a giant impact between Earth and a Mars-sized body called Theia roughly 4.5 billion years ago. Let me talk about one more thing that I find genuinely fascinating: the asymmetry of the Moon. If you look at the Moon, one side, the side that faces Earth, looks pretty different from the far side. The near side has large dark plains, the Maria, and lighter highlands, creating the pattern we recognize as the man in the Moon. The far side is much more crowded and doesn't have as many large Maria. For a long time, scientists weren't sure why the near side and far side were so different. This was actually one of the mysteries of lunar science until we had spacecraft that could map the far side. It turns out that the near side of the Moon happens to have thinner crust than the far side. The thinner crust on the near side made it easier for volcanic material to erupt from the interior and fill in large basins, creating the Maria. The far side has thicker crust, which made it harder for volcanism to reach the surface. But why would the crust be thinner on one side? This is still an active area of research, but one hypothesis involves the giant impact itself. The collision might have created asymmetries in the Moon's interior structure that persisted as the Moon cooled and solidified. The hemisphere facing Earth during the early stages might have experienced different heating and cooling rates than the far hemisphere. Another possibility involves the distribution of heat-producing radioactive elements. These elements, like uranium, thorium, and potassium, decay over time, releasing heat. If these elements were distributed unevenly in the Moon, it could lead to asymmetrical thermal evolution and thus asymmetrical crustal thickness. There's also the possibility that the Moon's interior underwent convection in ways that preferentially transported heat toward the near side, leading to more extensive volcanism there. Scientists are still working out the exact mechanism, but the point is that the asymmetry between the near and far sides of the Moon tells a story about the Moon's history and internal structure. And it's another detail that feeds into our overall understanding of how the Moon formed and evolved. All right, let me talk about the future of the Earth-Moon system, because it's actually kind of interesting to think about what happens over extremely long timescales. As I mentioned, the Moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year. That might sound incredibly slow, but over millions of years, it adds up. In a billion years, the Moon will be about 38,000 kilometers farther away than it is today. As the Moon moves away, its gravitational effects on Earth diminish. The tides will get weaker. Over billions of years, the tides will be noticeably weaker than they are today. Additionally, Earth's rotation will continue to slow. In the distant future, we're talking billions of years, a day on Earth could be as long as the current lunar month, roughly 47 of our current days. At that point, the Earth would be tidally locked to the Moon, with the same side always facing the Moon. But before that happens, the Sun will have evolved significantly. Stars like our Sun undergo gradual changes over their lifetimes. As the Sun ages, it gradually gets brighter. This brightening is called the faint young sun paradox in reverse. When the Sun was young, it was actually dimmer than it is today, which raises questions about how Earth stayed warm enough for life. But as the Sun ages, it gets progressively brighter. In about 1 to 2 billion years, the Sun will have gotten bright enough that Earth's surface temperatures will become inhospitable for most current life forms. The greenhouse effect will intensify. Oceans will evaporate. The atmosphere will become dominated by water vapor and carbon dioxide. Life as we know it will become impossible. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. It will undergo a dramatic transformation, expanding into a red giant. In this state, it will be so large that it will probably engulf Mercury and Venus. Earth might escape being engulfed, depending on the exact details of the Sun's evolution, but Earth will be far too hot for any life. The oceans will have long since boiled away, and so the Earth-Moon system, as it exists today, will eventually come to an end. Not because of the Moon moving away. That process would take far longer than the Sun's remaining lifetime, but because of the Sun's evolution. So the habitable window for Earth is finite. It's measured in billions of years, but it's not infinite. We're currently about 4.5 billion years into Earth's history, and we probably have somewhere between 1 and 2 billion years left before the Sun's increasing brightness makes Earth uninhabitable. That's actually one of the reasons why thinking about space exploration and the long-term future of humanity is important. If we want the human species, or life in general in some form, to persist beyond Earth's habitable window, we'll need to figure out how to leave Earth and establish life on other worlds. And the Moon will likely play a role in that. The Moon is a potential stepping stone for human expansion into the solar system. It's close enough to be accessible with relatively modest technology, but it's far enough away to be genuinely challenging. Learning how to live and work on the Moon will teach us lessons that apply to living on Mars or the moons of Jupiter and Saturn. So the Moon, which formed from a violent collision 4.5 billion years ago, might end up being crucial to the long-term survival of humanity or life in general. That's a kind of poetic connection. The Moon enabled life to develop on Earth through its stabilizing effects, and then in the distant future, it might enable life to survive beyond Earth. Okay, here's something I want to circle back to that connects to our earlier discussion about the rarity of habitable planets. If the giant impact is necessary for moon formation, and if a large moon is important for climate stability, then how does this change our expectations about finding habitable exoplanets? In the past few decades, we've discovered thousands of exoplanets. Some of them are in the habitable zones of their stars, the regions where liquid water could exist. We often describe these as potentially habitable. But if we add the requirement that a potentially habitable planet should also have a large moon formed through a giant impact, we're adding a significant constraint. Not all planets in habitable zones will have such moons. Some will be moonless. Some will have small moons that don't provide the same climate stabilization. This doesn't mean these moonless planets can't support life. They might. Life is resilient and adaptable, but they might be less stable environments. Their axial tilt might vary more dramatically over long timescales. Their climates might be less predictable. Their tides might be weaker. So when we're searching for potentially habitable exoplanets, we might want to prioritize those where we can detect evidence of large moons. Or if we can't detect moons directly, we might want to look for indirect signs, like periodic variations in the planet's brightness caused by moons passing in front of the star, or gravitational signatures. Actually, there's a fascinating theoretical study that looked at what habitable exoplanets without large moons might be like. The research suggested that such planets could experience much larger variations in axial tilt over geological timescales. They might undergo dramatic climate swings, periods of relative stability alternating with periods of extreme climate variability. Life might still evolve under such conditions, but it would have to be more adaptable, more resilient to extreme changes. This has implications for the kinds of life we might expect to find on exoplanets. On Earth, life has evolved under relatively stable climatic conditions, at least on the timescale of individual species. But if we're looking at planets with unstable climates, we might expect to find life that's adapted to dramatic variability. Actually, Earth's climate has varied more than we might initially think. There have been ice ages, periods of extreme heat, volcanic winters caused by massive eruptions. But the moon's stabilizing effect has probably prevented the most extreme scenarios from occurring. Scenarios where the axial tilt swung wildly, or where climate feedback spiraled completely out of control. So the moon isn't just enabling life passively by creating stable conditions, it's actively protecting life from potential catastrophic climate changes. This is another reason why the moon is so important. It's not just a pretty object in the sky. It's a fundamental part of the system that makes Earth habitable. Now let me address one more misconception that sometimes comes up. The idea that the moon somehow came from Earth in the sense of being ripped away from it. This is sometimes called the fission hypothesis, and it's actually a pretty old idea. Some early planetary scientists thought that the moon might have formed by a large chunk of material being somehow torn away from Earth, perhaps by tidal forces from the sun or some other mechanism. But this hypothesis has serious problems. First, the angular momentum doesn't work out. If a chunk of Earth were torn away and went into orbit, the angular momentum of the system would be different from what we observe. Second, the chemical composition is too similar. If a chunk of Earth were ripped away, you'd expect it to have a composition identical to Earth's mantle, which isn't quite what we see in the moon. Third, there's no known mechanism that could accomplish this kind of fission, so the fission hypothesis has been essentially abandoned. The giant impact hypothesis explains the observations much better, but it's interesting that people still sometimes think of the moon as coming from Earth in some sense. In a way, they're not entirely wrong. The moon does contain a significant amount of material that came from Earth's outer layers. It's just that it also contains material from Theia, and the process that brought them together was a giant collision, not a gradual separation. All right, let me talk about one more aspect of this that I find genuinely compelling: the precision of the conditions that led to the current Earth-Moon system. The giant impact had to happen at the right time. If it happened much earlier, Earth's composition would have been different. If it happened much later, Earth might have already cooled too much for the impact to have the right effects. There's probably a window of time, maybe a few 100 million years, during which the impact could have occurred and still produced a habitable result. The impactor had to be the right size. Too small, and the impact wouldn't eject enough material to form a moon. Too large, and the impact would completely destroy Earth. The range of sizes that could work is probably fairly narrow, maybe a factor of 2 or 3 in either direction. The impact angle had to be right. A head-on collision would have completely destroyed Earth. A grazing collision might not eject enough material. An oblique impact at the right angle seems to be what happened, and this particular angle range might be relatively narrow. The impact velocity had to be in the right range. Too fast, and the interaction is too violent. Too slow, and there isn't enough energy to eject material. The 4 to 6 kilometers per second range seems optimal, and the composition of Theia had to be similar enough to Earth's composition to explain the isotopic signatures we observe. This suggests that Theia formed in the same region of the solar system as Earth, or that at least the material they were made of came from the same sources. When you consider all these constraints together, you realize that the current Earth-Moon system is the result of a remarkably specific series of conditions. If any of these parameters had been significantly different, we'd have a different moon, or no moon at all. And if we had a different moon, or no moon, Earth might not be habitable. This is sometimes called the fine-tuning problem or anthropic principle, the observation that many parameters in the universe seem fine-tuned for the existence of life, and particularly for the existence of intelligent observers like us. There are different ways to think about this. One perspective is that it's just luck. Among all the possible ways a planetary system could form, Earth ended up in one of the configurations that's conducive to life. We wouldn't observe ourselves in a universe where life wasn't possible, so we naturally find ourselves in a universe with just the right parameters. Another perspective is that maybe there are many universes with different parameters, and we naturally find ourselves in one where life is possible. This is called the multiverse interpretation, though it's quite speculative. Or maybe there's something about the laws of physics that makes life-supporting configurations more common than we'd expect by chance alone. Maybe there are deep principles we don't yet understand that naturally lead to the formation of habitable planets. I don't know which of these perspectives is correct, and they're all somewhat speculative. But it's worth thinking about the fact that our existence depends on a long chain of unlikely events that all happen to work out in our favor. All right, let me wrap up by returning to where we started. The idea that you can look up at the moon in the night sky and understand something about your own existence. The moon is more than just a celestial object. It's a record of events. It's a necessity for a record of events. It's a necessity for life as we know it. It's a potential future home for humanity. It's a constant presence that has shaped human culture for as long as humans have existed, and we now understand how it came to be, through a giant impact that happened billions of years ago, an event so violent and so unlikely that it shaped the destiny of an entire planet. That's a remarkable achievement of human knowledge, that we can look at something as familiar as the moon and understand its deep history, that we can use physics and chemistry to reconstruct events that occurred before any observers existed to see them. The moon in the night sky is a reminder of how much the universe has to tell us, if we're willing to listen, and how much of our own story is written in the cosmos around us. You know, there's one more aspect of this that I think is worth exploring: the role of chance versus inevitability in how Earth became habitable. When we think about the giant impact, we could see it as pure chance, a random collision that happened to work out well for life. From this perspective, we're incredibly lucky. Most planetary systems probably don't experience giant impacts at just the right parameters. Most planets probably don't end up with large, stabilizing moons. We won the cosmic lottery. But there's another way to think about it. Maybe giant impacts aren't as rare as we think. Maybe they're actually a fairly common part of planetary system formation. If that's the case, then maybe many planetary systems go through a giant impact phase. Maybe the formation of large moons through giant impacts is more frequent than we'd initially expect. In fact, some simulations of planetary formation suggest that giant impacts might be relatively common. In a young solar system with lots of planetary embryos, collisions are almost inevitable. Most of these collisions might be destructive or produce poor outcomes. But statistically, some of them will happen at just the right parameters to produce habitable results. If that's true, then the existence of habitable planets with large moons might not be as unlikely as it initially seems. It might be a natural consequence of how planetary systems form rather than a rare accident. This is actually still an open question in planetary science. We don't yet have a complete understanding of how frequently giant impacts occur in young planetary systems or how frequently they produce habitable outcomes. But it's an interesting possibility that the giant impact that created our moon might not be a once in a billion chance event, but rather a fairly common occurrence in planetary formation. If that's true, then habitable planets with moons might be more common in the universe than we'd otherwise expect. That would have implications for the search for extraterrestrial life. It would suggest that the conditions that enabled life on Earth, including the stabilizing presence of a large moon, might be replicated on many other worlds. Here's another thought. The giant impact might have had effects that went beyond just creating the moon. When a Mars-sized body collides with Earth, the energy released is absolutely enormous. We're talking about energy equivalent to millions of megatons of TNT. This energy would be distributed throughout Earth's structure. Some of it goes into ejecting material that becomes the moon, but some of it also goes into heating Earth's interior, accelerating Earth's differentiation, creating currents in Earth's mantle. The impact might have triggered or accelerated processes that would have happened anyway, but more slowly. For example, Earth's magnetic field is generated by convection in the liquid outer core. The giant impact might have energized this convection, strengthening Earth's magnetic field in the early solar system. Why does that matter? Because Earth's magnetic field protects the planet from solar wind, charged particles streaming from the sun. Without a magnetic field, solar wind would strip away Earth's atmosphere over time. So a stronger magnetic field in the early solar system would have meant better protection for Earth's atmosphere. This has implications for habitability. If the giant impact strengthened Earth's magnetic field, then in addition to creating the moon and stabilizing the climate, it might also have protected Earth's atmosphere. It would have been a triple benefit for habitability. Of course, this is somewhat speculative. We don't have direct evidence that the giant impact significantly strengthened Earth's magnetic field, but it's plausible based on what we know about how giant impacts affect planetary interiors. There's also the possibility that the giant impact affected Earth's internal composition in ways that had long-term effects. When material is vaporized and recombines during a giant impact, it can undergo chemical reactions that wouldn't normally occur. Some scientists have speculated that the giant impact might have affected the distribution of certain elements in Earth's interior, which could have had effects on Earth's long-term chemical evolution. Again, this is somewhat speculative, but it illustrates how the giant impact might have affected Earth in multiple ways beyond just creating the moon. Now, let me talk about something that's kind of philosophically interesting, the idea that the moon is receding from Earth. Most people think of the moon as a permanent fixture. It's always been there. It will always be there. But mathematically and physically, the moon is in the process of leaving us. Over hundreds of millions of years, it will get progressively farther away. Eventually, it will be so far away that total solar eclipses will no longer be possible. The moon will appear smaller and smaller in the sky. This is actually a kind of poignant thought. Humans have experienced and been fascinated by lunar eclipses and solar eclipses for all of recorded history. Ancient peoples developed sophisticated astronomical knowledge partly to predict and understand eclipses. Modern people still find eclipses to be awe-inspiring events. But eventually, in maybe 600 million years or so, the moon will be too far away for its shadow to reach Earth during a solar eclipse. The moon's angular size in the sky will be smaller than the sun's, so it won't be able to completely block the sun's light. That chapter of Earth's astronomical history will be closed. Of course, by the time that happens, other things will have changed. Life on Earth will probably be very different from what it is today. Humans might not even exist anymore, or might exist in forms we can't currently imagine. But the idea that we're living in a relatively unique period, a period when the moon is large enough in the sky to completely eclipse the sun, is kind of neat to think about. It's another reminder that we exist in a specific moment in cosmic history. Not at the beginning, not at the end, but somewhere in the middle, with a particular configuration of celestial bodies that won't last forever. All right, let me talk about the implications of the moon's existence for how we think about the future of life in the universe. If large moons are important for habitability, and if large moons form through giant impacts, then this suggests that habitable planets might often have experienced violent pasts. They're not gentle, peaceful worlds that slowly formed in quiet isolation. They're worlds that have been through collisions, upheaval, and transformation. In some ways, that's a kind of encouraging thought. It suggests that habitable worlds are resilient. They can survive giant impacts. They can turn potentially catastrophic events into events that enable habitability. There's a kind of robustness to the process, but it also suggests that the path to habitability is not straightforward. It requires not just the right distance from the star, not just the right size and composition, but also the right cosmic history. A planet has to be in the right place at the right time to experience the right kind of impact that creates a moon. This has implications for how we search for life. When we look at exoplanets, we might not just want to ask, is it in the habitable zone? We might want to ask, does it show signs of having experienced a giant impact? We might look for moons as indicators of habitability. In fact, some scientists have proposed that the presence of a large moon should be considered a biosignature, a sign that a planet might be habitable, not in the sense that the moon itself contains life, but in the sense that its presence indicates the planet has the right conditions for life. This is an interesting twist on how we think about biosignatures. Usually, we think about biosignatures as chemical signs, like oxygen in the atmosphere or methane. But the moon is a planetary biosignature in the sense that its existence correlates with conditions that enable life. Now, here's something I find really fascinating: the fact that we can infer things about exoplanet systems just by understanding our own system. 50 years ago, we only knew about one planetary system, ours. We didn't have examples to compare to. We didn't know if our solar system was typical or unusual. We couldn't make generalizations about how planets form. Now we know of thousands of exoplanetary systems, and we can compare them to ours. We can say things like, Most planets orbit closer to their stars than Earth does, or most stars have multiple planets. We can identify patterns, and by understanding how our moon formed, we can make predictions about exoplanetary systems. We can say, if a planet has a large moon, it probably experienced a giant impact similar to the one that created our moon. We can use the physics and chemistry we've learned from studying our own system to understand distant systems. This is the power of science. Understanding one system deeply gives us insight into many systems. Okay, let me address one more question that sometimes comes up. Could Earth have formed without a giant impact? Could we have ended up without a moon? In principle, yes. If the giant impact hadn't occurred, Earth would still exist. It would just be different. It would probably be rotating faster than it currently does, with shorter days. Its axial tilt would probably vary more over time. Its climate would probably be less stable. Would life still have evolved? Maybe. Life is adaptable, but it would have evolved in a different environment. The emergence of life might have been harder without stable tides to concentrate chemicals in tidal pools. The evolution of complex life might have been hindered by a less stable climate. The emergence of intelligent life, and thus observers who could contemplate their own existence, might have been much less likely. So in a sense, the existence of intelligent life on Earth depends on the giant impact. Not just human life, but any intelligent observers who could look up at the sky and wonder about the cosmos. This is sometimes called the anthropic principle, the observation that we can only exist in a universe that's compatible with our existence. We wouldn't be here to observe a universe without the right conditions. So naturally, we observe a universe where the giant impact happened, where the moon was created, where life emerged and evolved. But that doesn't mean the giant impact was inevitable. It was a contingent event, something that happened but didn't have to happen. From that perspective, our existence is dependent on luck. We're here because of a specific chain of unlikely events. At the same time, if those events are not as rare as we might think, if giant impacts are a relatively common part of planetary formation, then intelligent observers might be fairly common in the universe. There might be many worlds where contingent events all align to create habitable conditions and enable the emergence of intelligent life. Once the moon solidified, it became something Earth could never be, a witness. Because the moon lacks plate tectonics and an atmosphere, its surface is a fossilized record of our shared history. It holds the scars of the late heavy bombardment, a period about 4 billion years ago when the inner solar system was pummeled by a storm of asteroids. While Earth's geological activity erased the evidence of this violence, the moon's craters tell us exactly when and how hard our neighborhood was hit. To understand the moon's surface is to read the diary of Earth's most violent childhood years. We don't know yet, but these are fascinating questions to contemplate. Let me talk about one final aspect: the role of the moon in human space exploration and what that might mean for the future. The moon is close enough to be accessible with current technology, yet far enough to be genuinely challenging. This makes it an ideal testing ground for technology and techniques that we'll need for more ambitious space exploration. If we eventually want to go to Mars, we need to know how to land on another world, how to conduct scientific research, how to survive in a hostile environment. The moon is a place where we can learn these skills. The moon is a practice ground for Mars, but the moon might also be a destination in itself. Some people envision a lunar base, a permanent human settlement on the moon. A base would serve as a scientific research station, studying the moon and the cosmos, but it could also serve as a launching point for further exploration, a pit stop on the way to Mars or beyond. There's also the possibility of lunar resource extraction. The moon has minerals. The moon might have water ice in permanently shadowed craters. An advanced civilization could potentially mine these resources and use them for space-based industries. Some scientists have proposed that the moon could become the hub of a space-based economy. Spacecraft could be built on the moon, launching from the moon into space. Solar panels on the moon could generate electricity. The moon could become a kind of industrial park for space. This is all speculative, of course. We don't yet have the technology for any of this, but it's interesting to think about how the moon might fit into humanity's future. And all of that possibility, the potential of the moon to serve as a base for human expansion into space, to enable humanity to reach for the stars, traces back to an event billions of years ago, a giant collision that created the moon and made Earth habitable. In a way, the moon's entire history, from a violent birth in a collision, through billions of years of geological activity, to its current role as a stabilizer of Earth's climate, has been leading to this moment. A moment when intelligent observers on Earth have developed the capability to leave their world and explore the cosmos. And the moon is positioned perfectly to help us do that. There's something almost poetic about that narrative arc. The moon made life on Earth possible, and now life on Earth might use the moon to spread beyond Earth. The moon that created the conditions for us might help us transcend those conditions. That's a beautiful way to think about the deep connection between Earth and its moon, and the role both play in the story of life and consciousness in the universe. There's something else worth exploring here. The way scientific understanding of the moon has evolved over time, and what that tells us about how science works. For most of human history, the moon was simply there, a mysterious object in the sky. Ancient astronomers could observe it, track its cycles, predict its phases and eclipses, but they had no way to know what it actually was, how it formed, or why it existed. Then, with the development of telescopes, we could see more detail. Galileo saw craters and mountains. Scientists realized the moon had a complex geology, but we still didn't know how it formed or why its geology looked the way it did. For centuries, the prevailing hypothesis was that the moon had been captured by Earth's gravity, that it had formed elsewhere and was somehow trapped in orbit. This made intuitive sense. If two objects are in space and one has more gravity, it could pull the other into orbit. It seemed plausible, but then, as we developed more sophisticated tools, better telescopes, spectroscopy, radio astronomy, we started getting hints that something was wrong with the capture hypothesis. The moon's composition seemed too similar to Earth's. The isotopic ratios didn't match what you'd expect if the moon had formed elsewhere in the solar system. Then we sent spacecraft to the moon. We orbited it. We landed on it. We brought back samples. And those samples provided the crucial evidence that overturned the old hypothesis. The isotopic analysis of those samples showed that the moon had to have formed from material that was chemically similar to Earth's material. It couldn't have been captured from somewhere else. And yet, the chemical composition wasn't identical to Earth's mantle, which ruled out simple co-accretion or fission. So scientists had to develop a new hypothesis, one that could explain both the similarity and the differences. The giant impact hypothesis did exactly that. It explained why the moon's composition was similar to Earth's, because it contained material from Earth, but not identical. because it also contained material from Theia. This is how science works in practice. You have a hypothesis. You test it. New evidence contradicts it. You develop a better hypothesis that explains more of the observations. You test that hypothesis. Over time, through this process of conjecture and refutation, you get closer to understanding what's actually true. The giant impact hypothesis didn't come out of nowhere. It was developed by scientists trying to make sense of data that didn't fit older theories. It's a good example of how scientific revolutions happen, not through sudden inspiration, but through the gradual accumulation of evidence that old ideas can't explain. And it's also worth noting that the giant impact hypothesis wasn't universally accepted immediately. When it was first proposed in the 1970s, it was controversial. Many scientists were skeptical. It seemed too dramatic, too violent. Some still preferred the capture hypothesis or other alternatives. But over time, as more evidence accumulated, more scientists became convinced. Computer simulations showed that the giant impact could produce results consistent with observations. Isotopic analysis became more sophisticated and confirmed the chemical similarities. We developed better understanding of planetary formation, and giant impacts fit naturally into that understanding. By now, the giant impact hypothesis is the consensus view among planetary scientists. Not everyone agrees with every detail, but the basic idea that the moon formed from a collision between Earth and a Mars-sized body is widely accepted. This actually brings up an interesting point about how we know things scientifically. We don't have absolute proof of the giant impact. We can't rewind time and watch it happen, but we have overwhelming evidence from multiple independent sources: isotopic data, orbital mechanics, computer simulations, our understanding of planetary formation. All of this evidence points to the same conclusion. That's how science works. We gather evidence, we look for patterns, we develop theories that explain the evidence, and we update those theories as new evidence emerges. We don't achieve absolute certainty, but we do achieve reasonable confidence that we understand how things actually work. Now let me talk about something that's kind of interesting from a historical perspective: the Apollo program and what it taught us about the moon. The Apollo program was driven by geopolitical considerations, the space race between the US and the USSR. But it also generated enormous amounts of scientific knowledge about the moon. Apollo astronauts brought back 382 kilograms of moon rocks. That's a massive amount of material to study. Those samples were analyzed by scientists all over the world. They were cut up, examined under microscopes, subjected to isotopic analysis, studied with every technique available. The data from those samples fundamentally changed our understanding of the moon. In particular, the isotopic analysis of the Apollo samples provided the evidence that convinced most scientists to accept the giant impact hypothesis. Without those samples, we might still be debating whether the moon was captured or formed in place or originated some other way. This is a fascinating example of how practical space exploration and scientific understanding are connected. The Apollo program wasn't primarily designed to test the giant impact hypothesis. That hypothesis hadn't even been fully developed when Apollo started. But the samples brought back by Apollo provided exactly the data that scientists needed to test and accept the hypothesis. There's a lesson there about the value of exploration. Sometimes we explore because we have specific questions to answer, but sometimes we explore and discover things we weren't expecting, things that change how we understand the world. The Apollo samples are still being studied today. Scientists continue to analyze them with new techniques. Just a few years ago, new insights about water in the moon came from reanalyzing Apollo samples using modern spectroscopy techniques that didn't exist when the samples were first collected. This suggests that future lunar exploration, bringing back new samples from locations we haven't sampled before, could generate new insights we can't currently anticipate. All right, here's something that connects back to the habitability discussion: the relationship between the moon and Earth's magnetic field. I mentioned earlier that Earth's magnetic field is generated by convection in the liquid outer core, but the moon also affects the core indirectly. The gravitational pull of the moon creates tidal forces not just on the oceans, but on the entire Earth. These tidal forces cause the solid parts of Earth to deform slightly. The crust and mantle stretch and compress as the moon passes overhead. These deformations are small, but they're measurable. This deformation generates heat through friction. It's called tidal heating, and it's the same mechanism that keeps the subsurface oceans of Europa and Enceladus warm and liquid. On Earth, the amount of heat generated by tidal heating from the moon is relatively modest. It contributes maybe a few percent to the total heat flowing from Earth's interior. But it's not negligible. Some scientists have speculated that the moon's tidal heating might help maintain the convection in Earth's outer core that generates the magnetic field. If that's true, then the moon isn't just stabilizing Earth's climate through its gravitational effects on obliquity, it's also contributing to the maintenance of Earth's magnetic field, which protects the planet from solar wind. This is still somewhat speculative. The exact contribution of tidal heating to core convection isn't definitively established. But it's another example of how the moon's influence on Earth goes beyond just the obvious effects like tides and seasons. It's another reason why the moon is important for habitability. Not just one reason, but multiple reinforcing reasons. The moon stabilizes the climate. The moon creates tides that might have concentrated chemicals in the early Earth. The moon might contribute to maintaining the magnetic field. All of these factors together make Earth more habitable. Let me talk about one more aspect of planetary formation that's relevant here: the late heavy bombardment. After the giant impact that created the moon, Earth continued to be bombarded by asteroids and comets. This bombardment was especially intense during the first few 100 million years, a period called the late heavy bombardment. During this time, Earth was being hit by large bodies on a relatively regular basis. These impacts would have been devastating. They would have vaporized oceans, created massive explosions, and made conditions on Earth's surface extremely hostile to life. Yet, despite this bombardment, evidence suggests that life emerged on Earth sometime during or shortly after the late heavy bombardment. We don't have perfect evidence. The geological record from that time is fragmentary, but chemical signatures in ancient rocks suggest the presence of biological activity. This raises an interesting question. How could life emerge and persist during a time when Earth was being bombarded by asteroids? One possibility is that life emerged multiple times. Maybe it emerged, got wiped out by an impact, and then emerged again. This could have happened multiple times until conditions became stable enough for life to persist. Another possibility is that life emerged in protected niches, deep underground, or in hydrothermal vents, or in other locations where impacts wouldn't immediately destroy it. Life could have emerged in these protected environments and then expanded to the surface once the bombardment subsided. A third possibility is that the bombardment was actually beneficial for life in some ways. Incoming asteroids and comets contain organic material and water. They might have delivered some of the chemical ingredients necessary for life to emerge. The heat from impacts could have powered chemical reactions. The impacts might have created conditions that were actually favorable for life's emergence, even while making conditions difficult for life to persist. This is still an active area of research, and we don't yet fully understand how life emerged during such a hostile time. But the point is that the early Earth, freshly formed from a giant impact, battered by ongoing bombardment, is where life somehow got started. That's kind of remarkable. Life emerged not in a peaceful, stable environment, but in a chaotic, violent one. Life is more resilient than we might think, and the moon might have played a role here too. The moon's gravitational effects would have affected the orbits of incoming asteroids and comets. It might have deflected some impacts. It might have altered the bombardment pattern. We don't fully understand the details, but the moon's presence would have affected the bombardment environment. So the moon was there from the very beginning of Earth's habitability story. It was there when the planet was being bombarded. It was there when life emerged. It's been there throughout all of Earth's history. In some sense, the moon is a constant presence that has shaped Earth's entire history. Not just in recent times, but all the way back to the beginning. Okay, let me address one more misconception that sometimes comes up. The idea that the moon causes the tides in the sense that the moon actively pulls water up. In reality, tides are more subtle than that. The moon's gravity does pull on Earth's water, but it also pulls on the entire Earth, the crust, the mantle, everything. The water responds to the gravitational gradient, the difference in the moon's pull on the near side of Earth versus the far side. On the near side, the moon's pull is slightly stronger than on the average. The water bulges toward the moon. On the far side, the moon's pull is slightly weaker than on the average. The water bulges away from the moon. You get two bulges, one facing the moon and one on the opposite side of Earth. As Earth rotates, different locations pass through these bulges, experiencing high tides when they're in the bulge and low tides when they're between bulges. The sun also contributes to tides, though less dramatically than the moon. Because the sun is farther away, its gravitational gradient is smaller. This mechanism is important for understanding tides. The tides aren't caused by the moon pulling up the water like a magnet. They're caused by the differential gravitational effect of the moon across Earth's diameter. Why does this matter? Well, it affects how strong the tides are. The strength of the tides depends on the moon's mass and distance. If the moon were closer, tides would be stronger. If the moon were farther, tides would be weaker. If the moon were significantly closer, say half its current distance, tides would be much stronger. This could have effects on ocean circulation, on coastal ecosystems, on the chemistry of water. If the moon were significantly farther, which will actually happen over billions of years, tides would gradually become weaker. This would affect ocean circulation and other processes that depend on tides. The current distance of the moon seems to be in a sweet spot, far enough that tides don't dominate everything and disrupt planetary systems, but close enough that tides are significant for ocean circulation and other processes. This is another example of the fine-tuning that characterizes Earth's system. The moon is at the right distance with the right mass to create tides that are beneficial without being destructive. All right, let me wrap up this extended exploration of the moon and its significance by coming back to something I mentioned at the beginning, the perspective that looking at the moon can give us. When you look at the moon in the night sky, you're looking at the product of a cosmic event that happened billions of years ago. You're looking at something that's essential for your existence. You're looking at a world, a place with mountains and valleys, with a geology and a history, with regions that were volcanically active and regions that have been frozen in time for billions of years. And you're looking at a future possibility. The moon might be where humanity goes next. It might be a stepping stone to the stars. It might be the beginning of expansion of human civilization beyond Earth. The moon connects the past, billions of years of cosmic history, to the present, this moment right now when you can look up and see it, to the future, possibilities we can barely imagine. That's a perspective that I think is worth cultivating. In our daily lives, we're often caught up in immediate concerns, but looking at the moon reminds us that we're part of something much larger. We're part of a planetary system. We're part of a solar system. We're part of a galaxy with billions of stars, in a universe with billions of galaxies. And our existence, improbable as it is, depends on a long chain of events that extends back to the formation of the solar system itself. There's something humbling about that perspective, but there's also something empowering. If we're here, if consciousness and intelligence emerged on this planet, then we have the capacity to understand how we got here. We can look at the evidence and reconstruct the story. We can use that understanding to make better decisions about our future. We can also use the moon itself as a symbol of possibility. When we see humans have walked on the moon, we know that we're capable of achieving remarkable things. We're capable of building technology, working together, pushing the boundaries of what we thought was possible. The Apollo program ended in 1972. For more than 50 years since then, no human has returned to the moon. In some ways, that's a shame. We had the capability, and then we stopped. But there are new programs now. NASA's Artemis program, China's lunar exploration program, private companies developing lunar landers. It seems like humanity is poised to return to the moon. And this time, instead of a brief visit, we might establish a longer-term presence. We might do the kind of extended exploration that wasn't possible with the earlier missions. When that happens, when humans return to the moon and establish a sustained presence, it will be another pivotal moment in human history. It will mark the beginning of a new phase of human expansion, and it will be enabled by our understanding of the moon's geology, composition, and potential resources. So the science of understanding how the moon formed and what it's made of isn't just interesting intellectually. It has practical implications for what we'll be able to do with the moon in the future. Here's one more thought about the moon that I find genuinely moving. The idea that the moon has been a constant witness to the entire history of life on Earth. For the last 3.8 billion years since life first emerged, the moon has been in the sky above Earth. It's been there through all the transitions in life's history. It was there when life was just simple microorganisms in the oceans. It was there when life moved onto land. It was there when dinosaurs roamed the earth. It was there when mammals evolved. It was there when humans emerged. The moon didn't change much during all that time. It was slowly moving away, slowly changing in appearance, but it was fundamentally the same moon, a constant presence, a stable feature of the world. And then, in the last few thousand years, humans started really noticing the moon. We developed cultures and mythologies around it. We tracked its cycles. We used it to organize our calendars. Artists painted it, wrote about it, composed music about it. The moon became embedded in human culture. And then, in the last century, we developed technology sophisticated enough to reach the moon. We went there. We walked on it. We brought back pieces of it. We studied it scientifically. In a sense, the moon has been guiding the history of life on Earth all along, creating the conditions for life to emerge and persist. And then, when life developed intelligence, when humans emerged and developed technology, we turned around and started studying the moon itself. We're now beginning to understand the very thing that made our existence possible. There's a kind of beautiful reciprocity in that. The moon enabled us. Now we're learning about the moon, and soon we'll probably return to the moon and make use of it for our own purposes. It's a story that spans billions of years. It's a story that connects physics and astronomy and biology and human history. It's a story that shows how everything is connected, how a violent collision in the early solar system shaped the destiny of an entire planet, and how that shaped the emergence of life, and how that shaped the emergence of intelligence, and how that intelligence can now look back and understand the very event that made it possible. That's the story of the moon. That's why when you look up at the moon in the night sky, you're looking at something that's much more significant than it might initially